Hello everyone, welcome to my class. In today's class, I will cover the integral test. So let me start the class right away. First, quick preview. The main questions for series we wish to answer: does the series converge or diverge? If it converges, what does it converge to? There are several tests to answer the first part of the questions. And for the second questions, in general, it is difficult to find the exact sum of a series. Keep in mind, the first finite terms have nothing to do with the convergence or divergence of a series. We always look for the tail of the series. Our convergent test deals with positive series, and the first test involves the improper integrals. Now let's start the integral test. Let me state, suppose f is a positive, continuous and decreasing on 1 infinite, and let an equals to f of n. Then the series an is convergent if and only if the improper integrals of fx from 1 to infinite is convergent. Great. So, quick side notes. The integral test can be used to show both the series convergent and divergent. So that means, let me state this last line of this statement. The series is convergent if and only if the improper integrals, the corresponding improper integral is convergent, or the series is divergent if and only if the corresponding improper integrals is divergent. Side note 2, it is important that f be eventually decreasing and not necessary to start the series or integral at 1. Alert: in general, sum of the series is not equals to the integrals. IV, same techniques from 7.8 apply to evaluate the improper integrals. An application of the integral test is to determine the behavior of the p series. Recall, for p not equals to 1, the improper integrals of 1 over xp from 1 to infinite equals to limit t tends to infinite, the definite integrals from 1 to t of x to the power negative p. Then I skip the step here, just evaluate these definite integrals and put the limit. It turns out to be limit t tends to infinite 1 over 1 minus p times, inside the parentheses, t to the power 1 minus p minus 1. The p series test. The p series of 1 over n to the power p is convergent if p is greater than 1 and divergent if p is less than or equals to 1. That means the harmonic series, which is series 1 over n, is the first p series to divergent. In other words, series of 1 over n to the p converges if and only if the corresponding improper integrals of 1 over x to the power p from 1 to infinite converges, and the series 1 over n to the p diverges if the corresponding improper integrals 1 over x to the p from 1 to infinite diverges. Quick example. The series 1 plus 1 over 2 times radical 2 plus 1 over 3 times radical 3 plus ... which equals to the summation n goes to 1 to infinite 1 over n times radical n. This equals to the series of 1 over n to the power 3 half converges, being p series with p equals to 3 half is greater than 1. Awesome. Now let's do some example. Worked examples. 1. Determine whether the given series is convergent or divergent. The series is n over n square plus 1. The summation runs from 1 to infinite. Great. So to apply the integral test, I need to show three things: positive, continuous, and decreasing. So let's assume our nth term is an equals to n over n squared plus 1, and let our corresponding functions just change n to x. So fx equals to x over x squared plus 1. Let me scroll down. The positivity is obvious, right? So now let's show the decreasing. So to show the decreasing, let me use this derivative idea. So take the derivative and show this derivative is negative. So use the quotient rule. So f prime x equals to denominator times derivative of numerator minus numerator times derivative of denominator over denominator square. And simplify, this gives us 1 minus x squared over x squared plus 1 outside square. And this quantity is negative for x is greater than 1. So for example, if you put x equals to 2, then 1 minus 4 over the denominator is always positive because there is a square. So only we are focusing on numerator only. So that means our function is decreasing. So clearly f is positive and also continuous, because being differentiable means the function is continuous, and decreasing on intervals 1 to infinite. Then by integral test, so let me scroll down. So by integral test, the improper integrals of fx from 1 to infinite equals to limit t tends to infinite, the definite integrals 1 to t of x over x squared plus 1. Then first let's evaluate the definite integral, then put the limit at the end. So in the next step, so just copy limit t tends to infinite, then use u substitutions. So put x squared plus 1 equals to u, then its derivative turns out to be 2x dx, or you can multiply numerator and denominator by 2. Then the numerator is 2x, which is the derivative of denominator. Then the integral of these fractions turns out to be natural log of x squared plus 1. Great. So limit as it is. We divide by 2, multiply by 2. So the 1/2 outside, the 2 from the denominator outside. And then the integrals of 2x over 1 plus x squared becomes natural log of x squared plus 1. And put limit x equals to 1 to t. Let me scroll down. And in the next step, so pull 1/2 outside the limit, so constant here. Then limit t tends to infinite. Put x equals to t, so ln t squared plus 1 minus, for lower limit, ln put x equals to 1, so ln 2. And now take the limit at t tends to infinite. The first term goes to infinite, so that means this whole expression goes to infinite. So that means our improper integrals diverges. That means by integral test the corresponding series diverges. Great. Now let's move on. Part B. The given series is n squared times e to the power negative n squared. Let's begin the solution. Here the nth term is an equals to n squared times e to the power negative n cubed. Let our function equals to change n to x, so x squared times e to the power negative x cubed. Then the positivity part is obvious. Now let's verify for the decreasing. So let's take the derivative. So f prime x equals to apply the product rule and simplify here. Then let's focus on this expression here. So the exponential function cannot be 0 or negative, so only focusing on my numerator here. So for x is greater than 1, this is decreasing. So that means put x equals to 1 here. So 2 minus 3 is negative 1 times positive 1 is negative 1. And you can put 2. So here the 2 cubed is 8 times 3 is negative 24, then plus 2 times 2. So it's still this is negative. So awesome. So clearly f is positive, continuous, and decreasing on the intervals 1 to infinite. Then by integral test, the improper integrals of fx from 1 to infinite equals to limit t tends to infinite, the definite integrals 1 to t of this function x squared times e to the power negative x cubed. Let me scroll down. Now this is a good candidate of u sub, so put u equals to x cubed, then its derivative turns out to be u equals to x cubed, means du equals to 3x squared dx, so divide both sides by 3, then we have x squared times dx turns out to be du over 3. Then in the next step, just take the integrals of e to the power negative u, which gives you e to the power negative u over negative 1. Then we already have a 1/3 as a the constant we pull outside, so that means this gives me this result here, and resubstitute the variables. So our final answer is here of this integral is limit t tends to infinite negative 1/3 times e to the power negative x cubed, then put limit x equals to 1 to t. Awesome. Let's move on. Then the next step, put x equals to t upper limit and put x equals to 1 lower limit and subtract those two result which we have here. Then take limit when t tends to infinite, e to the power negative t cubed goes to 0. So then we have only negative times negative positive 1/3 e to the power negative 1. So that means the improper integrals converges. Then consequently, by integral test, given series converges. Awesome. Let's move on. Let's do part C here. So the given series is 1 over n times natural log of n. Summation runs from 2 to infinite. Let's begin the solutions. Here, n equals to 1 over n times natural log of n. So let fx equals to 1 over x times natural log of x. To show decreasing, let's take a derivative. So apply the quotient rule and then simplify. Then we will get this expression here. So this expression, I don't need to worry about denominator. This is always positive. So only let's see what we'll get on our numerator here. So this is negative due to this minus sign. This is negative on the intervals 2 to infinite. We know ln1 is 0, so keep in mind. And the summation runs from 2 to infinite, so that's why I put the interval here 2 to infinite. Great. So clearly function is PCD, positive continuous decreasing on interval 2 to infinite. But here is a small trick here. So for our simplicity, without loss of generality, we take intervals e to infinite. Because we know when you evaluate ln in e, this gives us 1. So that's why I truncate slightly bigger than 2. So the value of e is 2.7182, blah, blah, blah. So let's take our intervals e to infinite. Then by integral test, the improper integrals e to infinite of fx equals to limit t tends to infinite e to t 1 over x times ln x, and it's a good candidate of u sub. So put ln x equals to u, then its derivative turns out to be du equals to 1 over x times dx. Then we can easily integrate. So this turns out to be limit t tends to infinite 1 over u is ln u, and put u equals to ln x again back. That gives us ln of ln x from e to t. Great. In the next step, evaluate x equals to t and x equals to e, and this expression turns out to be here. So limit t tends to infinite, ln of ln t minus ln of ln e. We know ln e is 1, so ln 1 is 0. This part gone. But this one, when t tends to infinite, ln infinite is infinite, so that means the improper integrals diverges. Hence, by integral test, the given series diverges. But in fact, this is true, by the way. The series of 1 over n times ln n to the power p converges if p is greater than 1, diverges if p is less than or equals to 1. Okay. Let's do part D. Our given series is 3n minus 4 over n square minus 2n. The summation runs from 3 to infinite. Let's begin the solution, just a routine computations. So let an equals to 3n minus 4 over n square minus 2n. And fx equals to, change n to x, 3x minus 4 over x square minus 2x. Factorize the denominator. So 3x minus 4 over x times x minus 2. Use partial fractions technique. Then we can rewrite this fraction equals to 2 over x plus 1 over x minus 2. Clearly, f is PCD on 3 infinite. So now here being a sum of such function here. So this function is continuous and this function is continuous. The constant functions are continuous and this is the linear functions. The first degree polynomial, they are continuous. So that means the sum of the two continuous functions is continuous. So continuity part is obvious. And for the decreasing, if we increase the x, then these are decreasing. So then by integral test, the improper integrals from 3 to infinite of fx equals to limit t tends to infinite. The definite integrals from 3 to t of 2 over x plus 1 over x minus 2 dx. Then next step, let's take the integral. So copy the limit as it is. This is 2 times natural log of x plus ln of x minus 2 from 3 to t. Put x equals to t, put x equals to 3 and simplify, and we know ln and put limit t tends to infinite. The first term goes to infinite, that means everything goes to infinite. That means the improper integrals diverges, hence the given series diverges. Let me scroll down. Let me do example 2. Determine whether the given series is convergent or divergent. Part A. The given series is summations n from 1 to infinite of radical n plus 5 over n cubed. So great. So now let's use our P series test to show the series convergent or divergent. So here, let me rewrite the given series equals to, I can distribute this n cubed to both of these numerator. So then I can rewrite given series equals to summations n runs to 1 to infinite of radical n over n cubed, this way, and plus summations of 5 over n cubed from n equals to 1 to infinite. And let's use laws of index here and bring this radical n means n to the power 1/2 in my denominator by switching the sign. So then this gives me n cubed minus 1/2, which is 3/2. So this should be 5/2. And then the next one as it is. And now here n to the power 5/2 is bigger than 1. So being a P series, this converges. And this also being a P series and P equals to 3 greater than 1 converges. And the sum of two convergent series also converges. That means the given series is convergent. Awesome. But we don't know it converges to what number, but it converges. Great. Part B. The given series is summations n equals to 1 to infinite of 1 over n cubed plus 1 over 3 to the power n. Let's rewrite this series. Then we can distribute this summation to each of these the terms here. So the first one is summation n equals to 1 to infinite of 1 over n cubed plus summations 1 over 3 to the n equals to 1 to infinite. Now the first one is a p series, p equals to 3 greater than 1, so converges. The second series is a geometric series with common ratio is 1 over 3, which is less than 1, again converges, and hence the given series is converges. Awesome. One final remark: do not get confused with the p series, whose form is 1 over np, with the geometric series, whose form is 1 over p to the n in summation. I'm just here and here. Pay attention. So this geometric series here. So let me talk about this geometric series here. So given series is 1 over p to the n equals to, let's put n equals to 1, or write in expanded form, which is 1 over p plus put n equals to 2, 1 over p squared plus 1 over p cubed plus 1 over p4 dot dot dot. Then take 1 over p outside, that means 1 left plus 1 over p left plus 1 over p squared left plus dot dot dot. Then this inside the parenthesis, this is the geometric series whose common ratio is 1 over p, which is less than 1 if p is greater than 1, which I done here. Then it converges, being a geometric series, it converges, and it converges to the sum, which sum is first term over 1 over common ratio. So then 1 over p times 1 over 1 minus 1 over p. Simplify, this gives us number 1 over p minus 1, and I put it back here. Great, for p is greater than 1. Here it's a quick example. The series 1 over e to the n and runs from 0 to infinite, which is same as summation n equals to 1 to infinite e to the power negative n in expanded form. This is 1 plus 1 over e plus 1 over e square plus dot dot dot. This is being a geometric series. Its first term is 1, common ratio is 1 over e, so its sum is first term over 1 minus the common ratio. Simplify, it gives us e over e minus 1, so this is a number. That means this geometric series converges since r is less than 1. Yeah, great. So we finished the first test for series to check whether the series is converges or diverges, and in the next class we'll study more tests. Thank you.